A very good morning, students. Today we will learn about a very important property which is called electron affinity of the elements present in the periodic table. So in this lecture I will be covering the topics like definition of electron affinity, then factors controlling the electron affinity values, then I will tell you about the periodic variation of the electron affinities, and at the end I will tell you about some of the related problems. So first let me tell you what is the definition of electron affinity. Electron affinity is the amount of energy released, or I should say changed, because sometime energy is required also, when one electron is added to the valence shell of an isolated gaseous atom to form an anion. So what is the meaning of that? We have a stable atom, a neutral atom. We want to add one electron in it. The atom, before adding the electron, we have to consider that the atom is in isolated gaseous state, because it should not have any interaction with other atoms. That's why we take it in a isolated state, and in gaseous state we know that it will not be having interaction as much as if it is in a solid or liquid state. So we consider it in isolated gaseous state, and then we are adding one electron in its outermost shell. So here actually, if after addition of electron the atom is stabilized, then some amount of energy will be released. This energy released, the amount of energy released, is called the electron affinity of that particular atom. And what happens as we are adding electron to the neutral atom? A negative ion will be formed. So the amount of energy released is called the electron affinity. As it is an energy term, so it is expressed in electron volt per atom or kilojoule per mole. So I have told you that if the formation of the ion is a favorable process, then the amount of energy released will be the electron affinity value, and the process will be exothermic. In some cases it may happen that energy is needed for this kind of transformation, for the transformation of atom A to a negative ion, and in that case the process will be endothermic. And another thing is that when we have already A minus, if we want to incorporate another electron in it, this process will also not be favorable because of the repulsion between the electrons, and then this process will be also a endothermic process. So now I'll discuss with you the key factors which affects the electron affinity values of an atom. So first, the size is very important. You know very well that all these kind of physical properties like electron affinity, electronegativity, ionization energy, all depends very much on the size of the atom, and the relation is electron affinity is inversely proportional with R. R means the radius of the species. So look at here, chlorine, bromine and iodine. If we go from chlorine to bromine to iodine, the size of the atom increases, and look at these electron affinity values. So first one, that is for chlorine, it is minus 349 kilojoule per mole. For bromine this is minus 324 kilojoule per mole, and for iodine it is minus 295 kilojoule per mole. That means the amount of energy released for the formation of chlorine to chloride minus is actually here in between these three atoms. This is the most favorable process because the amount of energy released is more in case of chlorine. When we form Br to Br minus, then the amount of energy released is minus 324 kilojoule per mole. That is, it is less than what we got in case of chlorine to chloride formation, and in case of iodine it is again less than bromine to bromide formation. That means what is happening, as the size is increasing, the amount of energy released is less. And why this is happening? Because you know that the distance between nucleus and the outermost cell is increasing as the size is increasing. So what will happen? The attraction force towards the electron we will be adding from outside will be also less as the size is becoming more. That's why the electron affinity value is becoming less as we are increasing the size. So this is the relation of atomic size with electron affinity. And in the periodic table, you know, we have the metals, that is alkali metal and alkaline earth metal in the very much left end, and the halogens are present in the right end. So when we move from left to right, the atomic size decreases, and that's why the electron affinity value increases. And this left side we have the metals. So metals will have less electron affinity value, and the non-metals, that is the halogens, will have the halogens, and other non-metals also will have more electron affinity value. So for example, I have given here for lithium the electron affinity value is minus 60 kilojoule per mole, and for fluorine the electron affinity value is minus 328 kilojoule per mole. So you can now explain the periodic trend also with the help of this dependence of electron affinity on size of an atom. Now I will tell you this. Now you have understood also that how the magnitude of electron affinity should be dependent with the nuclear charge. If the nuclear charge is more, so it will be able to attract the electron we are going to add from outside more. So the amount of energy released will be more. That means if the nuclear charge is more, electron affinity will be more. Now what is the dependence with the penetration effect of the orbitals? So what is the meaning of penetration effect? Any orbital which can go more closer to the nucleus is called having more penetration power, and the penetration power of ns orbital is greater than np, is greater than nd, and it is greater than nf because of the shape of these orbitals. So ellipticity of ns orbital is the most, and that's why it can go very close to the nucleus. So what is the dependence with electron affinity? If we add the electron which is going to the ns orbital of any atom, then the system will be more stabilized. So what will happen? The energy released will be more in that case. That's why electron affinity value will be more. So this will be the relation with the penetration effect of the orbitals with electron affinity values. So another factor is screening effect of the lower lying inner orbitals. So what is the dependence of screening effect with nuclear charge? If the screening is more, then the effective nuclear charge will be less. And as we know that the relation of electron affinity with nuclear charge is directly proportional. So what will happen if the Z star is less? That means it will not be effectively attract the electrons which we will be adding from outside to get the electron affinity values. And in this case the electron affinity value will be less. So if Z star is more, electron affinity will be more. So this will be the relation with the screening effect of lower lying inner orbitals with the electron affinity value of an atom. So now I am going to discuss with you a very important point or factor which governs the electron affinity value of an atom, and that is the electronic arrangement of the atoms. So you know very well that the half and full-filled electronic configuration has an extra stability compared to the nearly half or full-filled configuration. So what will be the effect on electron affinity value? If we have any half-filled or full-filled orbital in the starting atom, it will be very difficult to add one electron in there. So obviously the electron affinity value will be less. And if we have an atom where if we can add one electron and it goes to a configuration, the product is having a configuration of that of half filled or full filled, then the system will be stabilized because of the gaining of electron, and in that case the electron affinity value will be more. You see in this plot where electron affinity is plotted against atomic number, you see here the electronic configuration of lithium is 1s1, that of beryllium is 1s2. So if we add one electron in here, lithium 1s1, it will attain the configuration of beryllium, it will be 1s2, and this is a full-filled subcell. So what will happen? The electron affinity value of lithium will be more, but that of beryllium will be very less, because beryllium will not actually be stable if it gains one electron, and lithium will get a stable configuration. Again, coming to carbon and nitrogen, you see carbon has an electron configuration where it has at the end 2p2. So if we add one electron in here, it will become the configuration 2p3 like nitrogen. So what will happen? It will obviously try to go to this configuration after gaining one electron, and the system will be stabilized. So electron affinity value will be more. That's why we can see here that carbon has more electron affinity value. In case of nitrogen, as it has already a p3 configuration, it will be difficult to add one electron in that, and so the electron affinity value will be less. And same thing is present in this sodium magnesium pair. In sodium we have 3s1 configuration, so it will easily gain one electron, but in magnesium it will not get a stable configuration after gaining one electron, so it will have less electron affinity value. And the similar thing is present in case of silicon and phosphorus. Silicon is having 3p2 configuration and phosphorus is having 3p3 configuration. So now you can understand that how much this is important, the electronic arrangement of an atom, and how it dictates the value of the electron affinity of atoms. So now I will discuss with you about the periodic variation of electron affinity values. So here in this presentation, there are electron affinity values for some selected elements. Now you see, if we go from left to right in a period, the electron affinity value increases, and if we go down from top to bottom in a particular group, the electron affinity value decreases. And why this is happening? In my previous talks, I have discussed with you that how the size of the elements changes as we go from left to right in a periodic table. The nuclear charge is increasing, the electrons are getting added in the same cell. So what is happening? The ultimate effect is that there will be more attraction between the nucleus and the outermost cell, and the size will decrease in case of periodic movement. And as the size will decrease, so the attraction between the nucleus and the outside electrons will be more, and if the attraction is more, obviously the electron which we will be adding to get a negative atom, negative ion, will be more. So if the energy released is more and the system gets stabilization, we will have more electron affinity values. And in case of going down from top to bottom in a group, the size increases as the new cells are adding up as we are going from top to bottom. So although the nuclear charge is increasing, the effect of the increase of the number of cell is more prominent here, and the size will increase. As the size will increase, so obviously the electron affinity value will decrease, because the amount of attraction force exerted by the nucleus will be less, and for that reason the energy released to put one electron in the outer cell will be difficult, and obviously the value of electron affinity will be less. You can look at in group 1. There are a few exceptions are there actually in group 2, alkaline earth metals, and also here actually what is happening here we have a NS2 configuration, so it will be very difficult to put one electron in there. That's why you see the electron affinity values are positive. And in case of group 15, where we have a half-filled electronic configuration, here also you see the electron affinity values are very less. And in case of the group 18 elements, that means the noble gases, here also the electron affinity value will be very less. So for some of the elements it is positive, because these elements have a NS2 NP6 configuration, which is a full filled cell configuration, and for that it will be difficult to add one electron in there, and that's why the electron affinity values are very less. So here is a graphical representation of the electron affinity values with the atomic number of the elements. So here you can see some of the elements which are actually the electron affinity values are tending to nearly 0 for them. Like here you see the noble gases are here, helium, neon, krypton, argon, krypton, all are here. Then you can see that the group 2 elements like beryllium, magnesium, calcium, strontium, they are also having the electron affinity values near to 0. I have already told you about why this is happening so. And here one thing I wanted to tell you, in case of transition metal, the values of electron affinity values are not very regular, and for most of the elements we don't get the electron affinity values. But you will be surprised to note that the post-lanthanide element like gold has the electron affinity value highest among all the metals. And why this is happening? Because both D and F contraction are present in case of gold. Lanthanide contraction is very much prominent. So what happens for that? Gold acquires very small size, and the Z star becomes very high in case of gold due to the poor shielding effect of the D and F electrons. The nuclear charge is exposed towards the outer electrons, and the result is that gold can easily attract the electrons which we will put to get the gold Au negative ion. And the existence of Au negative ion is very well known. So now you understand that why gold can form a oride ion. And this is a question actually comes in the examination, that explain why gold can form Au to Au minus ion. So you will be able to answer this based on the electron affinity value of gold. Another important finding which I want to share with you is seen in case of group 16 and group 17 elements. For the first element of the group 16 and group 17, the trend is reversed. Trend means, you know, the electron affinity value, as we are going down, the size is increasing. So what will happen? The electron affinity value will decrease as the size increases. So electron affinity value will decrease. So from fluorine to chlorine, what happens actually? So fluorine should have more electron affinity value than chlorine, or here in between oxygen and sulfur, oxygen should have more electron affinity value than sulfur, but you see in this plot you can easily make out that fluorine is having less electron affinity value than chlorine, and oxygen is having less electron affinity value than sulfur. That means the trend is somehow reversed. So why this is happening? That is because of the small size of fluorine or oxygen. What happens, as they have very small size, if we want to incorporate another electron in here, there will be electron-electron repulsion. So this repulsive force will actually be acting in here, and so the electron affinity value will be less. So addition of electron will not be a favorable process in case of fluorine and oxygen. Here you see the values. So the electron affinity value for fluorine is minus 328 kilojoule per mole, whereas for chlorine this is minus 349 kilojoule per mole. So the value for chlorine is more than that of fluorine. So that means now you understand that why the values are reversed here, due to the electron-electron repulsion. The energy released will be less in case of fluorine and oxygen. So this is also a very popular question which comes in the examination, that explain why the electron affinity value of fluorine is less than chlorine, but the electronegativity value of fluorine is more than chlorine. Because electronegativity, in case of electronegativity, you know that elements are not accommodating any electron in its own cell. So electron pairs are there in the bonded condition and it is just attracting. So in that case, fluorine will be able to attract the electron pair towards it more, but it will be very difficult to accommodate one electron directly in the outer cell. So now I think you will be able to answer that question. So here are some problems, like why the electron affinity of chlorine is greater than fluorine, that already I have discussed with you. Then problem 2 is second electron affinity of oxygen and sulfur is positive, whether these supports the formation of CuO or CuS. So you see here in CuO and CuS, oxygen is O2 minus and sulfur is S2 minus. So this is basically an unfavorable process, because I have already told you, once we incorporate one electron, that is and negative, when a negative ion is already formed, it will be difficult to incorporate another electron to form the dinegative ion. And here these compounds CuO and CuS, you know very well that they are very stable compounds. So then how these compounds are forming? So this electron affinity or ionization energy, these are not only these factors actually dictates the formation of any compound. There are several factors as well. So like that, in these ionic compounds there is energy involved when these compounds are formed, which is called the lattice energy. When the ionic compounds form, a huge amount of energy is evolved, and which is called the lattice energy, and this lattice energy will help to overcome the second electron affinity value for these ions O2 minus and S2 minus. The unfavorable process becomes favorable, and that's why we can have very stable CuO and CuS, copper oxide and copper sulfides. So you will be able to answer these questions also. And again, I have already discussed with you that explain why, although Au is a metal, Au minus is a stable ion. So this is already discussed in the previous slide. So today we have learned the definition of electron affinity. Then we have also learned the factors controlling the electron affinity values. Then we have learned the periodic variation of electron affinity values, and I have also discussed with you some of the related problems, and I hope you will be able to answer the questions related to electron affinities now. So for today I am ending my lecture here, and many thanks to you for listening to my lecture. So see you in my next class.